The good news is that these last two talks will actually have some algebraic geometry in them, and hopefully indicate to you. I was feeling badly that I didn't really indicate just how much algebraic geometry goes into these studies, because we had to cover the beginning material first. But at least now we have 2 lectures where there can be some geometry. So this is going to be a lecture on compression genericity. And there's 2 issues that I want to address. 2 problems that we've seen in our study. One we just saw this morning, so I'll remind you, is that no equations for sigma r segre phi m minus 1 cross phi m minus 1 cross phi m minus 1 for r greater than 2m minus 1, or 2m minus 2 maybe. And the method I showed you goes up to 2m minus 3 this morning, but all variants of that method also have the same limit. Anything you can get by determinantal methods, by vector bundle methods, that I'm aware of, only goes up to roughly that range. So it's not that I don't know other equations, that I don't know other equations beyond that point. And the other problem is, even for tensors concise when ageneric with Strawson's commutator identically 0 and other conditions, you know, this n closed, and I forget, well, can still have large border rank. And the example was T with T of A star looking like this. So more precisely, T will be some A1 tensor B1 tensor C1 plus Bm tensor Cm plus the rest, let's say I equals 2 to m, j equals 1 to m over 2 lower bar, and k equals 1 to, m over 2 plus 1 to m, some t I j k a I b j c k. So that means that it'll fall in this lower corner, this piece here. So I'll write this as some t1 plus t2, where this t2 has large border rank. So another way of saying this problem is i.e. there's some hyperplane inside a dual such that T restricted to this hyperplane cross B star cross C star fails to be concise, or i.e. there exists this kind of, say, B prime and B star. Let me call this A prime. C prime and C star such that T restricted to A prime cross B prime cross C prime is identically 0, where this is of dimension m minus 1, this is of dimension m over 2, and this is of dimension m over 2. So this is where I think of T as a trilinear form. Does everybody understand the problem as I restated it? Now, of course, in doing the study, I'm free to change the roles of A, B, and C. So I want a condition that does not distinguish the three vector spaces. So we'll say this motivates the following definition. Let's say T is in, and let me just do the general case, A tensor B tensor C, which is just, CA tensor CB tensor CC, is, I'll say, A prime, B prime, C prime compressible if there exists A prime in A dual of dimension A prime is A prime, B prime in B dual, C prime in C dual, dimensions B prime and C prime. Such that T restricted to A prime cross B prime cross C prime is identically equal to 0. So I'm defining what it means for tensor to be compressible. So the first question is, when is this condition non-vacuous? It may happen that if I take A prime, B prime, and C prime sufficiently small, then even a generic tensor restricted to some very small space might be 0. So let's address that question. So of course, T in A tensor B tensor C gives rise to a hyperplane inside A dual tensor B dual tensor C dual. Because this is a vector space and this is the dual vector space. And to say that T restricted to A prime cross B prime cross C prime is identically 0 is the same as saying the segre of P A prime cross P B prime cross P C prime is contained in the hyperplane T perp. So we want to know about generic hyperplanes. What is the compressibility of a generic hyperplane? And this gives the answer. Oh, by the way, this is all joint work with Mateusz Michalek. Now that Jarek is not here, I can mispronounce his name without any. None of you speaks Polish, do you? So I can say his name as badly as I say it. Oh, but we have to erase that on the tape. Anyway, he knows who I am. A sufficient condition that a generic hyperplane H side P A star tensor B star tensor C star fails to contain a segre is that A prime plus B prime plus C prime is less than A prime squared plus B prime squared plus C prime squared plus A prime B prime C prime. And remark, I expect the sufficient condition is also necessary and I verified this, we verified it in the case that we originally were dealing with over there, that A prime, B prime, C prime is A minus 1 any B prime and C. So this was the case that we were dealing with before, sort of. And this is via Chern class argument. You'll see why in a moment. And the same Chern class argument will, in principle, work in general, but the calculation is a little annoying, so we haven't carried out the calculation yet. We may or may not in the future. If one of you would like to do it, that would be a very nice project. So we know how to count dimensions in algebraic geometry, and we know how to count expected dimensions. The usual trick is to use an incidence correspondence. So let's consider the map. Right, you know this about, well, anyway, if you don't know it, you'll know it now. So let's consider this kind of multiplication map from the Grassmannian of A prime planes A star across the Grassmannian B prime planes and B star across the Grassmannian of C prime planes and C star to the Grassmannian of A prime B prime C prime planes in A star tensor B star tensor C star. And that's just, you know, a triple A prime B prime C prime just will map to A prime tensor B prime tensor C prime. And notice that this map is injective. And let's let sigma denote the image. Right, so in particular, the dimension of sigma is what? Do you know the dimension of the Grassmannian? So it's the dimension of this space. A prime times A minus A prime. This dimension of sigma is A prime times A minus A prime plus B prime B minus B prime plus C prime times C minus C prime. And what we want to see is we want to construct an incidence correspondence. So consider the variety of flags of size A prime, B prime, C prime contained in the hyperplanes inside this space. So this has two projections. A hyperplane inside the dual space is the same as a point in the original space. And of course, this space also projects onto the Grassmannian of A prime, B prime, C prime planes inside here. So this is the Grassmannian of A prime, A, B, C minus 1 inside A star. Right? And sitting inside this Grassmannian is sigma. Sigma are these triples. And we want to know this, the fact that we want to know if the hyperplane restricted to this, we want to know if this Segre product is contained in this hyperplane, right? That's what we want to know. And we want to know when this will always happen, or when this will not always happen, more precise, is what we're really curious about. And so if for every t here, that is every hyperplane here, every t perp, there's something in sigma that maps to it, then the condition is vacuous. So we want to know, so we look at pi inverse of sigma contained in here, and we want to know when does this surject onto this space. Because if when we project it down and it surjects, then the condition is vacuous. And if the dimension of this is sufficiently small that it cannot surject, then we know our condition is a non-trivial condition, that a generic tensor will not satisfy it. Sorry, there's a lot of negation in this, so it gets a little... Right. But we're in good shape, right? So for any E in this Grassmannian, what is pi inverse of E? Well, this is the hyperplanes containing E. And this is a projective space, right? This is isomorphic to P of A tensor, B tensor C mod E perp, I guess. So particularly the dimension should be equal to whatever it should be, A, B, C minus A prime, B prime, C prime minus 1. It's the projective space. So this is of dimension ABC. This is of dimension A prime, B prime, C prime. And then I subtract 1. Where did this start here? And so dimension of pi inverse of sigma, since this is a fiber bundle, is this number plus that number. Right? So if this number, in order for the map to be surjective, this number must be greater than the dimension of this space, which is ABC minus 1. Thank you. Well, so these cancel. Where's the blue? And the minus 1s cancel. And then I guess I could move, I don't know why I did it, but I moved some of these over to one side. But this inequality is the same as that inequality, except now maybe I made a mistake here. No, because I want it to be strictly less, so I cannot have that surjection. Good. Questions? The sign is bad. So this will surject if this number is greater than this number. And so I want it to be less than this number.
I mean the red one and the original.
So let's do it. So this is A prime B prime C prime plus A prime A plus B prime B plus C prime C minus A prime squared plus B prime squared plus C prime squared, and I need this number to be less than 0.
A prime plus C prime sign is
right. My sign is off on this one.
ABC minus A
this one.
No.
No.
I think that for this one, the yellow one.
Yes?
ABC minus A prime plus.
Ah, yes, thank you. Yes. And in fact, yes, and that's what I had, just a line above. Okay, good. I just, yeah, it's a lot of lectures. Okay, so then everything is good. So now we have the numbers when we could potentially get some new equations. But so now we understand when this condition is a pathology. Okay? This condition is a pathology if this inequality is this inequality holds and we still have containment. But what we are interested in is how this pathology relates to the secant variety of the Segre variety. That's, I mean, some other day we may be interested in how this pathology relates to some other variety in our space, but this lecture series is about the secant variety of the Segre variety. So this proposition tells us that relationship, namely that if the border rank of T is less than or equal to A plus B plus C minus A prime plus B prime plus C prime, then we do have the pathology. P T perp will contain a Segre. Now, I don't know if this estimate is sharp. Maybe one can do a little better, but at least it is an estimate. So let's do the proof of this. This one's really easy. So again, it's sufficient to, since we're dealing with a closed property, can assume that the rank of T is that number. So let's write out T. This is some A1, B1, C1 plus A2, B2, C2. I dropped the tensor product signs. Plus, let's just call this number R. And so all these are some vectors in A. I don't know anything about their linear independence. And now let's choose, say, alpha 1 up to alpha A prime. In A, annihilating, well, a complementary set. So that's A1 up to A minus A prime. So we can kill off the first bunch of terms with that, and the span of this, the span of this will be our A prime, is the span. And then we'll choose beta 1 up to beta B prime, and their span will be B prime, annihilating B A minus A prime plus 1 up to B A minus A prime plus B minus B prime. And then choose gamma 1 to gamma C prime, annihilating C A minus A prime plus B minus B prime plus 1 all the way up to CR, where again R is this number. And we see that T restricted to A prime cross B prime cross C prime is identically equal to 0. So, any questions? So let's go back to the case. A equals B equals C equals M. Let's write A prime equals B prime equals C prime equals some M prime. This is a non-trivial condition if M prime is sufficiently large, namely using this, M prime plus M prime squared over 3 has to be greater than M. i.e., we get equations for sigma r on the Segre up to r about 3m minus 3 root 3m. Which, notice, is greater than 2m for m large. But still much, much less than anything resembling m squared. Needless to say, it's still linear. So the good news is we've detected conditions that would, in principle, enable one to prove varieties are not contained in small secant varieties all the way up to 3 times the dimension instead of 2 times the dimension. The bad news is these equations are given implicitly. To write them down as polynomials, we would have to use elimination theory, which is bad. But on the other hand, you can often, maybe by tricks, show that this condition fails to be satisfied. So challenge. Find an explicit tensor let's say T, not in, say, sigma, let's just say 2m. By this method. The method can, in principle, go further, but already to break that barrier of 2 would be very interesting. Now, unfortunately, there's some bad news. Matrix multiplication is very compressible. In other words, this non-compressibility is going to fail miserably for matrix multiplication. So, for example, so m, remember, m now is cn squared. So if we take m prime equal to already n squared over 2, compressible. Mn is m prime equal n squared over 2 compressible. In fact, A prime, B prime, C prime equal to n squared over 2, n squared over 2, n squared compressible. And for this, I can show a proof by picture. I take a matrix, I put zeros on this half, zeros on this half. I multiply it by a matrix which has zeros here and non-zeros here. And if I multiply any two such matrices, I get 0, so I can have anything I want here. If I restrict to this space, I get 0. The proof is Mn restricted to the product of these spaces. This is my A prime, B prime, and C prime is identically 0. So I don't even need to do any restriction here. I just chop off half here and half here, and all these are 0. In other words, or another way to say it is I just do x, set xi alpha equal to 0, alpha greater than n over 2, and y beta j equal to 0 for beta less than n over 2. Assume n is odd or something. And we get this. So the good news is we've gone beyond linear algebra. The bad news is twofold. So there's two pieces of good news. One is we've gone beyond linear algebra. Two is we've gone beyond this 2m barrier in principle. But there's also two pieces of bad news. One, we cannot actually carry out these calculations in practice, at least in general. And two, our original motivation in matrix multiplication, this is worthless. So this is kind of a mixed story here, but it's a new story. Any questions?
What the very means? You mean that is very complex?
Well, because most, this says, so for example, let's say, just say it was not, say mn were not n squared over 2 plus 1 compressible. So this is the first chance, because I already showed you if I go one less, I can compress it. Then we'd get the bound that the border rank of mn is greater than or equal to 3 times n squared minus 3 times n squared over 2 plus 1, which is 3n squared over 2 minus 3. This is worse than Strawson. So it's behaving like a tensor of very low border rank. Well, it's behaving, it has the same compressibility as a tensor of very low border rank, very low rank. That's what I mean. So I have a few minutes, then I can start the last topic of this series, which is something completely new, namely the geometry of algorithms. And so geometry of algorithms. So we have our matrix multiplication sits inside Cn squared tensor Cn squared tensor Cn squared, which we also think of as this U star tensor V star tensor W star tensor U. And so this group GLU cross GLV cross GLW acts on this point. Now, that means it also acts on the algorithms, acts on the expressions for Mn as a sum of R rank 1 tensors. So say I don't know what R is, so I just call it R. In the IE, let's say we have that Mn is equal to T1 plus T2 plus Tr, each Tj of rank 1. Let's call this group, say, GMN. And now let's say I have G in GMN. Well, this is an equality. So if I have G dot Mn, this has to be equal to G dot T1 plus Tr. So this is G T1 plus G Tr. But this thing here is just Mn. So maybe I should state what I want to state in the proper generality. Let's say I have a variety X sitting inside projective space. Our case, X is the Segre variety. And we're studying sigma R of X. Above it, we can form an incidence correspondence. Let me call it sigma R0 of X. So this is the points on an honest R secant plane, or a secant P R minus 1 to X. And above here, I have an incidence correspondence, which will be the set of pairs X, comma, V1, VR, such that X is equal to V1 plus VR, and Vj are in X. So this is the pair of the let's not use X, Z. So if I have a point Z inside here, the fiber over Z is the set of expressions. And maybe I want a quotient by permutations because I don't care about the order of the V1 up to VR. So this sits inside the secant variety of X cross PV R times, but then quotiented by permutations. And what I'm saying is, if I have, and here our point Z is matrix multiplication, and what I'm trying to say is that if Z is preserved by some subgroup GZ sitting inside GX, the group preserving X. So here GX is this GLA cross GLB cross GLC, and GZ is this GLU cross GLV cross GLW. Then GZ acts on pi inverse of Z on the algorithms. So it preserves this point, but in general it'll move. I'm sorry, I erased it. Let me put it down here. So we have G dot Mn is this is Mn. I get another decomposition because G preserves the Segre variety. So I'm moving around, so I have the fiber over Z. I could decompose into orbits under my group.
A is your tensor B.
Sorry?
ABC is this tensor space.
Yes, this is A, B, and C. Yes. So the Segre variety, my X, is invariant under changes of bases in A, B, and C.
So why do you consider this smaller group GZ?
So GZ, and of course GX is a subgroup of GLB, which is another point. So GZ is the group preserving my particular point that I want to decompose. Here it's the group preserving matrix multiplication. So I have two subgroups of the general linear group of my big ambient space involved. The one preserving my variety, and therefore it's secant varieties, and the one preserving the point that so here's my PV, here's my X, and here's my little Z. And my X lies in some sigma R of Z, sigma R of X. My Z lives in one of these. And when I have this small group act, it'll fix Z, but Z will lie on some secant line. It will not fix these 2 points. It will move these points around in general, and therefore I get different expansions of my point. See, if I have a generic point of a secant variety, at least in this small range that we expect, it should have a unique decomposition. And here we see that it's highly unlikely to be unique because there are no points or very few points on this variety that are in fact there's only one point on this variety that's invariant under this group. So any decomposition is going to be moved around by that group, and so we get a family of decompositions.
So what about the bigger group? Bigger group does not fix this matrix multiplication.
No, it does not.
It does not.
No, it completely destroys it. So the real group, the real interesting group is this GZ. Okay? Now already we learned some extreme facts about matrix multiplication that are quite shocking. Okay? Now what we really should look at is not just rank algorithms, but border rank algorithms, and that'll be my lecture tomorrow. So we should really kind of define some sigma R of X, which should be some kind of closure of this object. And you'll get into trouble if you take closure naively. So the best way to take closure here to avoid problems is to actually think of the triple. So of course here it's not going to make a difference. I'm going to do a triple Z, V1, VR, and then the span of V1, VR. So now this variety will sit inside PV cross R copies of X cross the Grassmannian of R planes in V. And then when I take closure, I don't run into trouble if I have this, because the closure in the Grassmannian will save me from having to blow up. It's basically the closure in the taking the point in the Grassmannian is effectively allowing me to do the Nash blow-up. So I'm basically taking the Nash blow-up of the naive Zariski closure. Okay? And so tomorrow, I'm going to study this space here. And the reason I want to study this space is I expect that the border rank of matrix multiplication is much, much less than the rank of matrix multiplication. And let me explain to you why. Because when I take an orbit, the orbit will not be closed, most likely. And I can look at its orbit closure. Its orbit closure will be on the boundary of this thing, will be a border rank algorithm. But also sitting inside this space, I have SR minus 1 of x kind of sits naturally in here. You could take some natural inclusion by any stupid way you want. And the codimension of this and this, let's see, do I have time to do the calculation? So let me do an exercise. The codimension of sigma r minus 1x, so x is the Segre, and z is matrix multiplication. The codimension of this, in this case, is almost equal to the dimension of gz, but not quite. Plus 1 or minus 1? Plus 1. Now, let's just say we didn't have this and that we didn't have any topology. So I'm going to make two simplifying assumptions, just a thought experiment. Okay, let's just say that this thing was a projective space. Of course it's not. It's much more complicated. And I have this subvariety, this SR minus 1. And let's say this 1 was in here. I have this other subvariety. If this were a projective space and that 1 weren't there, these two spaces would have to intersect the orbit. Assuming the action is transitive, which it is at least in the one case we know for sure. So matrix multiplication just misses being in this R minus 1. But the codimension here is, the calculation of the codimension here is independent of R. So then we could say, well, it actually has to be an R minus 2, and then R minus 3, and all the way down. So if this 1 were not here, or maybe it's the topology that saves us, matrix multiplication would be a rank 1 tensor. Because it has such an enormous symmetry group that its orbit closure barely misses hitting these smaller secant varieties. So that's the first remark. The second remark is that there's actually the group preserving matrix multiplication. If I identify U with V with W so that these three spaces are the same space, I think of matrix multiplication as an algebra acting on the same vector space, then there's a little bit of extra symmetry, cyclic symmetry, which we saw before, because trace of xyz is the same as trace of zxy, etc. Now this thing is more interesting. So there's an issue of continuous symmetries and discrete symmetries. And there's the Kamon Principle, due to Pierre Kamon. Well, the generalized, because he. So let's say I have a tensor in V tensor D. So our case, we have matrix multiplication inside Cn squared tensor 3. And let's say gamma is a subgroup of the permutation group. And gamma is contained in the group preserving T. Then T admits a gamma invariant optimal rank expression. So here, that would imply, so this is conjecture, I guess. Because it's not known to be true, except in very special cases. And here, this would imply that there should exist Z3 invariant algorithms. An exercise Well, it's too nasty as an exercise. Fact, Strawson's algorithm, viewed as a tensor, is Z3 invariant. So, using that, with Luca Chiantini, Christian Eichenmeier, and Giorgio Ottaviani, we actually had a purely geometric derivation of Strawson's algorithm and a description of this whole picture in the case of 2 by 2 matrix multiplication. That's available in these notes. But what I will talk on tomorrow will be a little bit more subtle. In general, we expect the best matrix multiplication algorithm to be on the boundary of this, in the closure of this thing, and not in the interior. And what has been recent with, again with Mateusz, but also with a graduate student, Nick Ryder, is not only did we develop a geometry of rank algorithms, but we've started to extend that to a geometry of border rank algorithms, a geometry of expressions as limits of rank R tensors. And if you think about that, if you're on the boundary here, what we really have is a curve in the Grassmannian such that for all time t greater than 0, say, the curve is spanned by r points of x, but the limiting point as t goes to 0, since the Grassmannian is compact, we know there must be a limit. That will contain our z, the matrix multiplication tensor, and the geometric study of border rank algorithms is the geometric study of these curves in Grassmannians. And so next time I'll show you just how beautiful the geometry of that is in the very simple case of the Bini algorithm that I began with on the first day. Thanks for your attention.